Video, we'll learn to calculate the total harmonic distortion in the case of a single phase inverter. Now we have a single phase inverter where the source voltage is at DC and we wanted to convert this DC voltage into an AC voltage. Now in the conversion process, the objective here is to know how much is the distortion of this output voltage from your required sinusoidal output voltage. Now we have an inverter circuit where if you turn on your switch S1 and S2, then your output resistance is connected across the source voltage, so you will have a positive voltage as your output. Now if you switch your S3 and S4 turn on, then you will have the negative voltage being connected across your output terminals, so you will have output voltage to be negative. So as a result, you will have for the half duration of time when you turn your switch S1 and S2 turned on, the output voltage exactly same as your source voltage. And now the next half of the time when you turned on your switch S3 and S4, then you will have your output voltage to be negative of your source voltage. Now, due to this switching process and the conversion circuit that we have, from the DC input voltage, we'll be able to get the square wave as an output voltage, but it is not a pure AC output voltage. Now, the objective here is to know the total harmonic distortion, which indicates how far this is close to our sinusoidal output voltage. Now, if we wanted to know how close this is to your sinusoidal voltage, then we can get it through a Fourier series expansion. Now, the Fourier series says that this square wave can be represented as the sum of multiple sine and cosine functions. Now, if you look at the Fourier series expansion, any waveform that you have like this can be represented as a function of A0, that is an offset DC, as well as the cos and sine waveforms. Now, if you wanted to know how is this A1 is being calculated, A1 is something that indicates the offset of this output voltage from zero levels. And now, since we have the output voltage as symmetric about the time axis, then we can indicate that it doesn't have any offset, or in electrical terms, we don't have any DC component, so the value of our A0 is equal to 0. So the next one is AN. AN is indicating how many cos functions can be incorporated in order to represent this square waveform here. Now, if you look at the output voltage waveform, this has half wave symmetry. So whenever your output voltage waveform follows the half wave symmetry, then it doesn't have any cos components. So when you don't have any cos terms, that is indicating that you have AN is equal to 0 for all values of n. Now, the only thing that we are left with is that output voltage or the square voltage can be represented as the sum of multiple sinusoidal voltages, multiple frequencies of the sinusoidal voltages. And now the question is, what is the peak value of every sinusoidal voltage? Now, if you want to know the peak value of every sinusoidal voltage, that is the value of Bn. Now, we know that the expression for Bn is available. Now, if you try to substitute the parameters of this square wave in the value of Bn, then you can see that the Bn, we have 2 upon T. The T is basically the time period of the waveform, assuming that we are switching on and off for the time period exactly same as the AC output voltage we wanted. So the duration of the AC output voltage we expect is 2 pi, so we say that the 2 upon T for us is 2 pi. And now integrate it over the time means we need to get the average value of this square waveform. If you want to get the average value of this square waveform, for that integration is from 0 to pi, we have an output voltage of VDC, because the f of t is basically VDC for us, and sine n theta, minus another half, we have output voltage as minus VDC, so we'll substitute that minus VDC here, and that is from pi to 2 pi. Now, if you integrate that and substitute your limits, then you get your Bn as 2VDC upon n pi multiplied by 1 minus cos n pi. Now, if your values of n are even, then you have your cos n pi for all the even values to be equal to 1. Now if cos n pi is equal to 1, 1 minus 1 will be 0 for us, then we have bn equal to 0, which indicates that for all the even values of n, your bn equal to 0. For odd values of n, you have your cos n pi value to be minus 1. In that case, you will have your bn to be 4vdc upon n pi, which indicates that you have your square wave represented as a function of only sinusoidal functions that corresponds to odd frequencies. So what are odd numbers for us is 1, 3, 5, 7, and so on. So now we understand that the Fourier series expansion of this square wave is just algebraic sum of various sinusoidal functions which are having odd frequencies. And now the peak value for every odd frequency is 4vd upon n pi. Now if you look at those, for n equal to 1, if you have your n equal to 1, then you have it as 4vdc upon pi. And now if your n equal to 3, then this is 4vdc upon 3 pi, which is indicating that if you say that this is v01, this is going to be v01 upon 3. Now for n equal to 5, then you will have it as 4vdc upon 5 pi, which is indicating that is equal to v01 upon 5. You know that when n equal to 1, that corresponds to a fundamental frequency of conversion that could be 60 Hz or 50 Hz. Now if you look at the n equal to 3, that is a third order harmonic, is having a peak value 1/3 of your fundamental frequency. Now fifth order frequency is having a peak value that is 1/5 of your fundamental frequency. Now if you look at the sine waves which are incorporated in order to represent your square wave here, they look like this. You can say that your peak value of the fundamental frequency, that is 60 or 50 Hz, is going to be 4vdc upon pi. If you say that this is v01, then the peak value of the third order sinusoidal frequencies waveform or third order harmonic is going to be v01 upon 3. And the peak value of the fifth order harmonic is going to be v01 upon 5. So now if you combine all these waveforms, that is when you will be able to represent your square wave. Though we started here with 1 and ended up with 5, if you go for higher and higher frequency, the accuracy of representing your square wave will be higher. So now if you try to plot the frequencies and the corresponding peak values on a plot, then you know that for the first order frequency, if you have the peak value as we indicated 4vdc upon pi, and then for the third order frequency, we have the peak value or the magnitude of that as 1/3 of your fundamental frequency. For the fifth order frequency, we have the magnitude as 1/5 of the fundamental frequency. That's what we see here. So now the seventh order, you can expand this and get to know that will have a magnitude which is 1/7 of your fundamental frequency. Now we know that your output voltage is expected to have only fundamental frequency and supposed to be a pure sinusoidal like this. But we have it as a square, which indicates that we have unwanted frequency components, which are the harmonics for us. Now, if you wanted to know how deviated is the square wave output voltage from the required fundamental voltage, that's where we have our total harmonic distortion factors. If you wanted to know how deviated is this square waveform from the fundamental frequency of 60 Hz or 50 Hz, then you can calculate that using the total harmonic distortion factor. Let's try to understand that total harmonic distortion using a simple example. Let us consider that you have an inverter for the source voltage of 100 volts and you are expecting your output voltage to be 60 Hz. And you have a load with a resistance of 10 ohm and inductance of 25 millihenry. Then if you try to represent the square wave output voltage of that inverter using multiple sinusoidal voltages, then the peak value of each frequency of voltage will be Vn equal to 4 multiplied by Vs, which is 100 for us, upon n pi. Now, you will have first order frequency component, third order, fifth order, seventh order, because we know that we will have only sine waves which are corresponding to the odd frequencies being present. Now, if you want to look at the RMS value of your output voltage as a whole, then it is just going to be Vs, because whether you have a pulsating or a pure DC, the RMS value of that is going to be exactly same, because it is root mean square of the voltage. So the RMS value of this particular voltage is going to be Vs. So now, if you want to get the total harmonic distortion, it is basically the square root of V RMS square, means the RMS of the total voltage, and how deviated is that total RMS voltage from the fundamental RMS, that is V1 RMS. Now, if you want to know what is the fundamental voltage RMS, then you know V1, the fundamental voltage that is embedded into this square wave, is 400 upon pi, that is when n equal to 1. So now you know V1 max, that is 400 upon pi, which is calculated as 127.3, peak value of the fundamental voltage. Then RMS value of that fundamental voltage is going to be V1 max upon root 2. So now you know that it has 127, where I'm saying that in the case of n equal to 1, V1, that is max value, is 400 upon pi. Now, if you calculate that 400 upon pi, that is 127.3. That's the max value of that fundamental frequency. And RMS value of that fundamental frequency will be 127.3 upon root 2. So now, this RMS value of this sine wave that you have embedded into this square wave is 127.3 upon root 2. So now, how deviated is this from the fundamental RMS? If you want to get to know that, then you can substitute the RMS value of the square wave, and its deviation from the fundamental RMS can be calculated as, you know, the RMS value of the fundamental voltage, and you know the RMS value of the total voltage. So how deviated is this total voltage RMS value from the value of the fundamental voltage RMS? You can calculate that using the total harmonic distortion, and you get to know that it is 0.483. So we have a significant deviation of this output voltage from the fundamental voltages. So how do we try to reach closer to the sinusoidal fundamental voltage? Is by eliminating the harmonics. So our objective here is to eliminate the harmonic components that we have, eliminate the third order, fifth order, and higher order that are close to the fundamental frequency, and get the pure sinusoidal voltage as our output as much as possible.